Welcome to the BKR chemistry classes. Today we are going to see chemical shift in proton and carbon NMR. So generally if I take ethanol, I'll be having three kinds of hydrogen. The hydroxy hydrogen, methylene hydrogen and the methyl hydrogen. If I look at this molecule, I say that hydrogens are H. So all the hydrogens should have the same excitation, same relaxation. But how do I have three different signals and three different positioning of the hydrogen in the proton NMR, or two different positioning of the carbons of ethanol in the carbon NMR? Now the question arises, why? Why do we have three signals for ethanol, and they are placed at three different values? What is the reason behind that? So, chemical shift means the shift in the signal based on the chemical environment. If a proton has a different chemical environment, it will give you a different signal that we already know. And where will the signal lie? So, we are going to discuss in this video regarding the positioning positioning of signals in proton NMR and carbon NMR. So the positioning of signal talks about the chemical shift which is given in delta in parts per million. So first let us see what is this chemical shift and why do the signals shift from each other in proton NMR and carbon NMR. So as I can see from this particular picture, the electron density around the hydrogens are different. So you can see here, this is the electron density chart for ethanol, and you can see the electron around the oxygen is the maximum, and you can see the electrons around this hydrogen has decreased, and also these hydrogens are less compared to the electron density around these hydrogens in a CH3. So these are CH3, these are the CH2 hydrogen, and this is the oxygen, and this is the hydrogen attached to the OH. Electron density around hydrogen, that is a proton is varying. So why is it varying? That depends upon the environment. That if I have electron withdrawing group near me, it will withdraw all the electrons from the hydrogens, and what will happen? The hydrogens become de-shielded. So here we bring in the concept of shielding and de-shielding. So if I say shielding or shielded, if I say shielded, the hydrogens are having rich electrons around them. If I say the hydrogens are de-shielded, that shows that the nucleus has less number of electrons around them. So de-shielded nuclei and shielded nuclei. So the electrons are shielding the protons. In this particular case, ethanol, you can see that the hydrogens of the CH2 are having less electrons around them compared to the hydrogens of the methyl. So methyls are away from the electron withdrawing effect of the oxygen here. So you have an oxygen here. So this oxygen has electron withdrawal effect. It withdraws the electron towards itself, but the effect is less pronounced towards the methyl because it is one carbon away from the oxygen. Whereas the methylene hydrogens, the CH2, methylene hydrogens are closer to the electron withdrawal effect of oxygen, therefore they are de-shielded. So we have less electrons here compared to. So here the electron density is bit higher. Okay. So when I talk about an NMR spectrum, I divide the NMR spectrum into two halves. One I say it to be right hand side and other I say it to be left hand side. So it varies from 0 to 10, or you can also go from 0 to 15. Left hand side of the spectrum, I say that the protons are in electron dense environment. So they have lot of electrons around them. So they are known as shielded protons. Whereas the left hand side, I say that protons are in electron poor environment. So the electron density around the protons is reduced. The electron density here is increased right hand side, but left hand side it is decreased. So they are known as de-shielded protons. So I'm talking about this shielding and de-shielding based on the electron density around them. If there are no electrons, I may not be able to differentiate them. Then I cannot study the proton NMR. So the electron forms a important part of studying proton NMR and also the carbon NMR. So, as I told you, in an NMR spectrum, I have two sides. I say the right hand side and the left hand side. Keep in mind that right hand side is having low delta values. So, they'll be having small delta values and they'll be having electron rich environment and they'll be shielded protons. Whereas left hand side will be having large delta values, they'll be closer to 10. And the protons will be having less electron around them and they'll be known as de-shielded protons. So as you move from 0 to 10, just keep in mind that you are moving towards a de-shielding zone. So you're moving from a shielding to de-shielding zone. Now the question arises why the protons which are shielded are known to resonate at low frequency and the protons which have less electrons around them are said to resonate at high frequency. So we have to answer to this question. As you can see from this particular energy diagram, so when I say that a spinning charged nuclei will generate a magnetic moment, okay, and they will behave like a tiny bar magnet. So when I put them into an external magnetic field, two things will happen. One is there'll be splitting of states, and not only that, they will be undergoing precessional motion. So this we have already seen. Okay, so same thing I've shown here. So when I put, so initially all the spins are will be in the same energy level. They'll be in the same energy level. But when I put into magnetic field strength, so here the B0, it's increasing. So when I put an extra magnetic field, I'll be having splitting of state. So I'll be having splitting of state. Now, how much is this energy splitting? This energy separation will depend upon what? That is important. So each hydrogen will be resonating at different frequency because they are split into different energies. Now, why they have different energy of splitting? So why they are split into different energies? That depends upon the electrons surrounding them. That this is the external magnetic field with a strength of B0. And I have two kinds of hydrogens. This hydrogen has less electron density around it, whereas this hydrogen has large electron density around it, high electron density around it. So red color I'm depicting as this electron. So now when I put them into an external magnetic field, we know that electrons also have a charge, they also have spin, so they will also generate a magnetic moment, and this magnetic moment generated, they will behave like a tiny bar magnet. And how will they behave in the external field? So generally the electron, the magnetic field will oppose the external field. So in this particular hydrogen, I'll be having a strong opposition from the electrons because I have lot of electrons around them. So this hydrogen will be having lot of opposition from the electrons because I have large electron density around them. Whereas this particular hydrogen, where there is less electrons, so this is the de-shielded hydrogen. De-shielded hydrogen. This is the shielded hydrogen. So the de-shielded hydrogen will have less opposition of the electrons towards the external field, whereas the shielded hydrogens will be having more opposition towards the external field. So it is like cancelling the external field. So they are opposing. So the magnetic moment or the field generated by the electrons are opposing the external field. So they will cancel the field experienced by the hydrogen. So this particular hydrogen will experience less field. And this particular hydrogen, the opposition by the electrons is less, therefore more field will go inside. So this hydrogen will experience more field. That is more of B0. Here you will be having less of B0. Why? Because the electrons surrounding the hydrogens are opposing the external field. They are opposing the external field, therefore less field will go inside. So here you will be having less field. Here you will be having more field going inside. So now we know that this energy separation is proportional to omega, the precessional frequency, Larmor precessional frequency. And since omega is equal to gamma into b0, where gamma is the gyromagnetic ratio, b0 is the external magnetic field, the delta E is proportional to b0. That suppose I keep for hydrogens, the gamma will remain constant. So the difference in energy depends upon the magnetic field which I experience. So the protons which are de-shielded, the green color proton which is de-shielded, will be experiencing more magnetic field. So since it will experience more magnetic field, the splitting will be higher. And this shielded hydrogens which is experiencing less magnetic field, this is experiencing less magnetic field, will be having less energy separation. Clear? Obviously. So I have two different types of hydrogens here based on the field which they are experiencing. So this particular hydrogens will be having larger separation of energy level, and this will be having less separation of energy levels. Is this point clear? So here I am having different separation of energy levels. So different separation of energy levels. So they are, this requires, so shielded protons requires less frequency for excitation. So after I separate them into energy levels, now they have different energy levels. So what will happen to the radiation frequency which is required for them to get excited from the lower state to the higher state? So the one which is having higher energy separation will require higher radio frequency, high frequency, because we know that delta E is proportional to the radio frequency which I am going to supply. So this particular de-shielded hydrogens will require more frequency for excitation because they have large separation. They have large separation. And this particular hydrogens which has less separation of energy levels will be require less frequency. Now we have differentiated. So this is what we were discussing. So when I talk about NMR spectrum, so I said it goes from 0 to 10 delta ppm. I'll come to this delta in short a while. So I have right hand side and I have left hand side. So right hand side we said it to be shielded, and left hand side we said it to be shielded. Shielded means you have more electrons surrounding the proton, and here you have less electron, and they have low delta value. They have low delta value. You have high delta value. And I said here you'll be having low frequency of resonance. Low frequency of resonance. Here you'll be having high frequency of resonance. So now we have got the point. So nuclei which is de-shielded, hydrogen which is shielded. So this will experience less B0, undergo less splitting. This will experience more B0. So de-shielded, shielded. The nuclei will experience more B0, it will be undergoing greater splitting because the delta E is directly proportional to B0. So now the radio frequency required will be high for a de-shielded nuclei, and the radio frequency required for excitation from the lower level to the higher level will be less in a shielded nuclei. That is why the shielded nuclei come at low frequency and the de-shielded nuclei come at the high frequency. You can see I am able to differentiate the hydrogen based on the electrons around them. So there is shift in the values of their excitation frequency based on the electrons around them. So if I have less electrons around them, I'll be having more field will they'll be experiencing. They'll be requiring high frequency for excitation. Whereas if they have more electrons around them, they'll be experiencing less field and they'll be requiring less frequency. So low frequency for shielded protons, high frequency for de-shielded protons. So now we have done the separation of zones. So zonal separation we have done. So we have shielding zone in the right hand side of the spectrum and we have de-shielding zone in the left hand side of the spectrum. So from 0, if I move towards left hand side, I'm getting de-shielded progressively. So progressively I'm getting de-shielded. So if I am closer to 0, I'm slightly de-shielded. When I go away from 0, I become more and more de-shielded. Have you understood this concept? Very, very, very important concept which you should understand. Without this particular understanding, you cannot really appreciate the problem solving. So, as we have seen, the right hand side, the shielded nuclei experience or sense a smaller effective magnetic field. So, they come into resonance at a lower frequency. And the protons that sense a larger effective magnetic field will come into resonance at a higher frequency. Is that clear? I should have a reference which should be placed at 0 such a way that from the reference I can try to assign the delta value for the protons under question. The reference stands at the 0 delta value, and from this reference, I position the different hydrogens in the molecule. Now, the reference commonly used is known as TMS, tetramethylsilane. So, see silicon attached to 4-methyl group. Now, since silicon is highly electropositive in nature, it gives the electron towards the carbon. So carbon is more electronegative than silicon. Therefore, carbon pulls the electron towards itself. So as a result, what happens? The electron density around the methyl increases. So the carbon and hydrogens have high electron density around them. Why? Because the silicon has given the electron towards the carbon. So the hydrogens are known to be shielded in this case. They're known to be shielded. So they are so very shielded that they can be placed at a 0 delta value. So, among the most of the organic compounds, not all, among the most of the organic compounds, these TMS are shielded. So, the TMS hydrogens are shielded. So, compared to the hydrogens in most of the organic molecules, since the TMS hydrogens are shielded, they can be placed in highly shielded zone, that is the low delta value. So, I fix that as reference. So fixing TMS as reference one not only requires this shielding, it has other advantages so that it becomes the commonly used reference in proton and carbon NMR. The first point of advantage is that here you have 12 hydrogens. All the 12 hydrogens are equivalent. So I get an intense signal. I get an intense signal in the 0 delta. So I'm fixing the TMS at 0 and I get an intense signal at 0. So it will be never missed. Why it is intense signal? Because you have 12 hydrogens. So you have 4 methyl. So 4 3 is the 12 hydrogens. All the 12 hydrogen resonate at same frequency. They resonate at same frequency because they are chemically equivalent. And they give you a very sharp and strong signal. So, because of this, what happens is I have the second advantage. I can use small amount of TMS that is more than sufficient because since it is giving me a very intense signal, I can use small amount of reference. Third advantage being this TMS is soluble in most of the organic solvent. It is soluble in most of the organic solvent. So I can have compounds which will be more de-shielded than TMS, but they may not have all these advantages. So it is soluble in almost all the organic solvents. So if you have a compound which is soluble in THF, TMS is soluble. If your compound is soluble in DMSO, TMS is soluble. Chloroform soluble. DCM soluble. So it is soluble in most of the organic solvents. This is the third advantage. The fourth advantage is the TMS is inert, so that means that it will not react with your organic molecules. So organic molecules may have so many functional groups, so TMS will not react with them and make changes to the NMR spectrum. The fifth advantage is low boiling nature of TMS. Low boiling nature, so it has low boiling point. So the boiling point of TMS is around 27 degrees. So it is almost less than the room temperature. So it can easily evaporate after the NMR spectrum recording is done. So you can remove the solvent. You can remove the solvent if they are low boiling. Also, you can remove the reference from the sample, and the sample can be retrieved and it can be used for other studies. So there are so many advantages of TMS which makes it a best reference for NMR. Okay, so there are 12 hydrogens which are equivalent, so it gives you very intense frequency. Since it is giving very intense frequency, small amount is enough, and it is also soluble in most of the organic solvents. It is inert, so it will not react with the organic compounds. Since it's low boiling, it can be easily evaporated and the sample can be retrieved. So all these points of advantages makes TMS as the best reference for proton and carbon NMR. Now, the hydrogens which we are taking in the organic molecule will shift from the TMS. So there is shift in frequency. There is shift in frequency. Why there is shift in frequency? Already we have seen that depends upon the electrons surrounding the hydrogen. So TMS hydrogens are highly shielded. Now the compounds which we will take into consideration will be having de-shielding compared to TMS. Therefore, they'll be shifting from the 0 towards the 10. So this shift from the reference towards the de-shielding zone, okay, because of the chemical environment, it is known as chemical shift. So chemical shift means shift in the delta value or the resonating frequency of a proton based on the chemical environment. So shift due to chemical environment, that is what is known as chemical shift, not ordinary shift. So shift in the resonance frequency based on the chemical environment is known as chemical shift. And now this chemical shift, how do we calculate? So the difference in energy is equal to h nu, which is equal to h bar omega. Nu is equal to omega by 2 pi. So now this nu is equal to gamma B0 by 2 pi. This is the effective magnetic field felt by the nucleus. So B effective is equal to B0 into 1 minus sigma, where sigma is known as the shielding constant. Electron surrounding the nucleus is giving a shielding. It is acting against the external magnetic field, is opposing the external magnetic field, therefore it acts as a shield. It is giving shielding to the nucleus. So the actual field felt by the nucleus, we say to be effective, is equal to the external magnetic field into 1 minus sigma, where sigma is the shielding constant. Now substitute the same. So here it will be no longer B0, it will be B effective. So the frequency is equal to gamma into B0 into 1 minus sigma divided by 2 pi. Okay, so variation of frequency with external magnetic field is known as chemical shift. So this variation depends upon the chemical environment, that is what's known as chemical shift. So shift in the frequency based on the chemical environment is known as chemical shift. So the equation which relates the frequency and the external magnetic field is given here. So nu is equal to B0 into 1 minus sigma. Since the shielding constant appears after a negative sign, thus the decreasing shielding results in higher frequency. So as sigma decreases, the mu increases. So decreasing shielding causes higher frequency because the sigma enters the equation after a negative sign. Okay. And similarly, if you have increasing shielding, the nu will decrease because the sigma enters after negative sign. So as nu sigma increases, the frequency will decrease. So de-shielded nuclei will be having high frequency, shielded nuclei will be having low frequency. So this particular equation relates the frequency with the magnetic field. Very important equation. A easy one to remember or understand the concept. chemical shift is given in delta. Delta is equal to the frequency of the sample from the reference. So mu sample minus mu reference. So since the frequency is given in hertz, delta will be having the unit in hertz. So now what happens? This equation will be dependent on the spectrometer frequency. So I can have an 100 megahertz instrument or I can have a 600 megahertz instrument. So the instrument megahertz will vary. So if this megahertz varies, what happens? The delta value will also vary. So if I record a NMR in 100 megahertz, I'll be having a different value than recording in 600 megahertz. So it becomes very tedious for me to remember, okay, which instrument I'm recording, what will be the value. So remembering multiple values will become very difficult for me. So what they've done is they've given you a formula which is independent of the instrumental frequency. So the formula is delta distance downfield from TMS. It's nothing but mu sample minus mu reference divided by the operating frequency of the spectrometer. So your mu sample minus mu reference is given in hertz, and your instrumental frequency, the instrument frequency, operating frequency is given in megahertz. So hertz and hertz will cancel. So you'll be having the 10 power 6 at the denominator. So I'll be having delta nu by mu of the instrument into 10 power minus 6. So this becomes delta nu by nu of instrument in parts per million. So that is why delta is given in parts per million. Delta is obviously dimensionless, it does not have a dimension, and also it does not depend upon the spectrometer frequency. So the delta value is equal to the difference in the frequency between the sample and the reference. The reference we are using here is TMS divided by the frequency, that is the operating frequency of the instrument in megahertz. Don't forget. So that is your chemical shift. So why the name chemical shift? The shift in the positioning of the proton based on the chemical environment. That is why it's known as chemical shift. Factors which influence the chemical shift or affect the chemical shift. First factor is inductive effect. The first factor is inductive effect. So if you have the CH3 hydrogen attached to an heteroatom, as you increase electronegativity, suppose I take chlorine, bromine, and iodine. So we know that fluorine is more electronegative. Therefore, the CH3 protons attached to the fluorine or the carbon attached to fluorine will be more deshielded, more deshielded compared to the CH3 attached to the iodine, because iodine is less electronegative. Okay, so the CH3 hydrogen and the carbon will be less deshielded. So compared to the reference, it will be deshielded, but the effectiveness of deshielding will be less for iodine compared to fluorine. Okay, so this is inductive effect. So if I take CH3F, CH3Cl, so if I compare the methyl halides, you can see that as I move down, the electronegativity is decreasing. So as a result, what will happen? The delta value will also decrease because iodine is less electronegative than fluorine. So this is basically the inductive effect. The second factor is resonance effect. Let me take a small example. Suppose I have CH2 double bond CH, C double bond O ethyl, and CH2 double bond CH O ethyl. So ethoxy group, and I have an ester group. Now see that here you have resonance effect. So here, since C double bond O is a minus R group, it will withdraw the electrons away from the double bond. Here, since you have OET, lone pair of electrons, so it will be acting as a plus R group, electron donating group. This is electron donating group. This is electron withdrawing group. When I compare the electron density of these two CH2, that is the CH2 of this particular carbon will be carrying a positive charge. So let me write the resonance structures first. So I'll be having CH2 plus CH double bond O OET, and here I'll be having CH2 minus CH double bond O plus ethyl. Now you can see that this carbon carries a positive charge and this carbon carries a negative charge. So the hydrogens here are de-shielded. So hydrogens here are de-shielded, and here the hydrogens are shielded because they have a negative charge. They have more density of electrons here. You have more density of electrons here. You have less density of electrons because the electrons have been removed by the electron withdrawing group. So they are having less electron density. They are de-shielded here. They are highly shielded. Highly shielded. So what will happen since they are de-shielded? They'll be having high delta value. Since they are shielded, they'll be having low delta value. So this is the effect of resonance. So resonance will vary the chemical shift values of the hydrogens or carbon for that matter. Because of resonance, if the hydrogens are deprived of the electrons, they'll be de-shielded, and if they get more electrons, they are shielded. If I take a benzene ring, I take a nitro group, and I take another benzene ring, and I take an amino group. You have guessed what I'm just planning to say. So, amino group lone pair of electrons acts as a plus R group, nitro group acts as a minus R group. What will happen? It will withdraw the electrons away from the benzene ring. Here, it will give the electrons towards the benzene ring. So here it is ortho-para-directing, this is meta-directing. Here why it is ortho-para-directing? Because ortho and para position become negatively charged. They get high electron density. Here it is meta-directing because the ortho and para position get the positive charge. Therefore, the meta has more electron density compared to ortho and para. Therefore, the electrophilic substitution electrophilic substitution takes place in meta position for electron withdrawing group. It takes place in ortho and para position for electron donating group. So the concept is you have high electron density. So the hydrogen in ortho position and para positions are shielded here because you get a negative charge. You get a negative charge in ortho and para position. Whereas the hydrogens of this particular molecule are de-shielded. Why they de-shielded? Because you get a positive charge in ortho and para position. So when I compare the chemical shift of the meta hydrogen, ortho hydrogen, para hydrogen of nitrobenzene, the meta will be less than the ortho and para because shielding gives you low delta value. Now among the ortho and para, the ortho hydrogens will experience the minus I effect and minus R effect. The para hydrogens away from the influence of the nitro group, therefore they'll experience the minus R group, whereas the ortho will experience both minus I effect and minus R effect. So when I compare the hydrogens, so the ortho hydrogens will be having greater chemical shift compared to the para hydrogen, then comes your meta hydrogen. This is the case for nitrobenzene. Now let us check for the aniline. So in this case, the para and ortho are shielded, but the ortho hydrogens will be experiencing minus I and plus R. Because you have NH2, nitrogen more electronegative, so it will experience minus I effect. Whereas para will experience only the plus R effect. So when I compare the shielding and de-shielding, so the para will be highly shielded compared to ortho, and meta is de-shielded. So the value will be de-shielded is meta, so it will be having the higher delta value. Then comes the ortho because we have minus I effect, and then comes the para which has the lowest value. So shielding is para is more shielded than the meta. Okay. So this is the second effect. The third factor is anisotropic effect. The third factor is anisotropic effect. So as the word says anisotropy, so it is different in different directions. So let me consider with an example. Suppose I take a benzene ring. Suppose I take a benzene ring. So when I put this benzene ring into an external magnetic field, when I put it into an external magnetic field, so this is external magnetic field. So what happens is that the ring current of the benzene always lies perpendicular to the external magnetic field. So this is the benzene ring. So it will lie perpendicular. So it will be lying flat on the external magnetic field. Okay. So if this is a ring current, if this is a ring current which is generated, this ring current will generate a secondary magnetic field which will go like this. So this is a secondary magnetic field generated, and this secondary magnetic field aligns the external field near the protons, outer protons. Aligning means it is giving more field to the protons, so it becomes de-shielding. And opposing means whatever is present here. If you have an hydrogen in the center, here we don't have, but I'm saying you'll be having shielding in the inner proton. Outer protons will experience a de-shielding zone because the secondary field is aligning with the external field. So you'll be having more field. So I have external field, I have this field, both will be given to the nucleus. So I'll be having more field experienced by the proton. So it will be de-shielded. Okay. So let me take a simple example to explain this for the inner and outer proton. Let me take 18 aniline. So in 18 aniline, you have 12 outer hydrogens, which I have labeled in green color. I have 6 inner hydrogens, which I have labeled in blue color. Now, as we have aromaticity here, so you have 18 pi electrons. So you'll be having a very strong ring current, and this ring current will generate a secondary magnetic field. Generate a secondary magnetic field in such a way that near the outer protons, it is aligning. The secondary magnetic field aligns near this outer protons and it is opposing near the inner protons. So align means it is de-shielding, and opposing means it is shielding. So already we have mentioned electrons around a nucleus opposes the external magnetic field. It shields the nuclei. Okay, so if you're opposing the external field, you will shield the nuclei. When they align with the field, okay, so here it is aligning with the field, so it will be shield. If you're opposing with the field, so you can see it is opposing, so it is shielding the hydrogen. So the inner hydrogen, 6 hydrogens will be shielded, and the 12 outer hydrogens will be de-shielded. So the shield hydrogen will be having low delta value. It is around minus 3.0. And the 12 hydrogens, outer hydrogens will be de-shielded. They'll be having high delta value. They have a value of 9.0. So the shielded protons have delta value less than TMS, and the de-shielded hydrogens have delta value more than TMS, highly de-shielded 9.0. If I have an alkene, even alkene, when put in the external magnetic field, it the pi electron current, if they are going like this, so they stand perpendicular to the external magnetic field. This is the B0, and the secondary field. Again, what happens? So it is they are flat. Okay, this molecule is flat. Okay, they align near the protons. So align. So as I told, align means it is de-shielded. Okay. Last one, if I take acetylene. If I put this acetylene into external magnetic field, what happens? So the pi electron current is going like this. Okay, the pi current, always the current pi current will be perpendicular to the external magnetic field, and this will generate a secondary field like this. And the secondary field near the protons, they are opposing the external field. So they are opposing the external field, therefore they are shielded. They are shielded. Okay. So when I compare an alkene and alkyne, so alkanes are sp3 hybridized, alkene are sp2 hybridized, and alkyne are sp hybridized. The percentage of S character is 25, 33, and 50. So as the S character increases, the electronegativity of the carbon increases, so it becomes more electron withdrawing. So if that is the case, the hydrogens attached to an sp3 hybridized carbon will be having more electron density than compared to the alkene hydrogen, then compared to the alkyne hydrogen. So if that is the case, the alkyne hydrogen should be more de-shielded. They should have the highest delta value. So based on this, I will say that the delta value should increase. But what happens? The alkane has a value of 0.522, alkene has a value of 426. So alkyne, I should expect a higher value, but it comes around 223. The reason being the anisotropic effect. So because of the anisotropic effect, the secondary field generated by the Acetylene pi electron current opposes the external field, so it is undergoing shielding. So because of shielding, it will be having low delta value. It comes around 2 to 3, whereas alkyne has high delta value because the secondary field generated aligns near the hydrogen, so they are de-shielded, they'll be having high delta value. So this is what is known as anisotropic effect. Okay, so that can be also observed in the aldehyde. Okay, so aldehydes, even in alkanes, even in cyclohexane system, you can refer to these molecules to know more. So the three factors which influence or affect the chemical shifts are inductive effect, resonance effect, and the anisotropic effect. So this is the typical proton NMR chemical shift value. So the alkanes will be ranging from 0 to 2. Okay, so you'll be having from 0 to 0. It will not go near 0. It will be like point 0.3, point 0.5, like that. And now the CH, the protons attached to a carbon followed by alkene, or the CH3 or CH attached to an aromatic ring, a CH attached to a carbonyl, or a hydrogen of the acetylene, that is acetylic hydrogen, all that will come around 2 to 3. So these four categories. So remember this, very important. So the CH3 or CH2 or CH attached to an alkene carbon, a CH attached to an aromatic carbon, a CH attached to a carbonyl carbon, and the acetylenic hydrogen. So hydrogen directly attached to acetylene, triple bond. They all will come around the range of 2 to 3. And now the hydrogens attached to an heteroatom, it can be nitrogen, oxygen, halogen, they'll come around 3 to 4. If you have methyl iodide, they'll come around 2.6, 2.5. So it will be lesser than 3. But in general, 3 to 4 corresponds to the hydrogens, carbon attached hydrogen attached to an heteroatom. Alkene hydrogens, that is alkene attached to the sp2 hybridized carbon, that will come around 4 to 6. Then you have aromatic region. Aromatic region ranges from 6 to 8. Aromatic ranges from 6 to 8. Then you have an aldehyde. Aldehyde will be above 8, that is around 9. You have aldehyde hydrogens. Then about 10, you have acid hydrogens. Okay, so very simple to remember. Very simple to remember. Alkanes. So hydrogen attached to primary carbon, secondary carbon, tertiary carbon, they'll be having slight de-shielding here. So they'll be having 0.9 to 1.4. Generally, they'll be ranging from zero point 0.5 to 2. Okay, then CH3 attached to C double bond O, the acetylenic hydrogens, all that will come around 2 to 3. And the hydrogen attached to an halogen atom will be around 3 to 4. So you have heteroatom, you can have oxygen, nitrogen, all that stuff will come around 3 to 4. Then you have alkene hydrogen, which will be around 5 to 6. Then you have CH3 attached to its alkene C double bond C, it will be around 2, 2.3 something. So the hydrogen attached to benzene ring will be around 7.2, so it's benzene. Generally, aromatic will be from 6 to 8. Then you have a CH3 attached to the benzene ring will be 2.3, 2 to 3. Then you have aldehyde hydrogen 9 to 10. Then you have carboxylic hydrogen 10 to 12. Now this OH, the alcoholic OH, the phenolic OH, and the amines, they are known as variable. So they'll be exchangeable. So exchangeable protons, so they'll be exchanging with the solvent, therefore they'll be having variable. They'll range from 2 to 5, 4 to 7, and 1.5 to 4. So generally, this exchangeable protons can be tested using the deuterated water. So if I have water H2O, deuterated water is D2O. So I can exchange this OH, exchangeable hydrogen, with D2O. So when I do that, I'll be having the formation of OD, the exchangeable hydrogen will be replaced by deuterium, and I'll be having something known as HOD peak. This HOD peak will be in the range of 4 to 5. Okay, so 4 to 5, or 4.5 to be very precise. So you can easily find this exchangeable protons by doing the deuterium exchange. So on deuterium exchange, you'll get HOD. This HOD will be around 4.5. Okay, so you can easily identify them. So these are the typical values. So once again, shall we have a quick revision? Alkanes from 0 to 2, attached to an heteroatom will be around 4. Then alkene will be 4 to 6. You'll be having aromatic from 6 to 8. Aldehyde will be above 8, that is around 9. And acid, carboxylic acid protons will be about 10, that is 10 to 12. And a CH3 attached to a aromatic ring, CH3 attached to an alkene, a CH3 attached to C double bond O, and the alkyne hydrogen. All these will come around 2 to 3. Very simple. So I have just split them into different categories, and we can easily remember them. Is it not? Okay. Now let's quickly look into the delta values of carbon. So alkane carbons, very simple, comes from 0 to 40 or 5 to 40. The carbon attached to heteroatom will be around 60. The alkyne carbon will be around 90. The alkene carbon will be around 110. Aromatic carbon 130. And you have C double bond O carbon which will range from 160 to 210. And I'll give you an important clue here. Suppose you have a ketone that will be greater than 200. That is a clue in most of the problems. Okay, so how to remember? Alkane carbon, so 5 to 40. Then, so carbon attached to heteroatom will be around 60. So if you have an heteroatom attached to carbon attached to halogen, nitrogen, oxygen will be around 60. And depending on the electronegativity will be having the range. So from 40 to 60 will depend on the range of which heteroatom you have attached. So it goes beyond 60 means it's very strong electron withdrawing group. That is an oxygen atom like that. Then you have alkyne carbon will be having 90, alkene carbon will be 110, aromatic carbon 130, and you'll be having the C double bond O. C double bond will correspond to carboxylic acid, ester, amide, acid chloride, aldehyde, all that put together, anhydride, all that put together. It will range from 160 to 210, and specifically if you have a ketone, you'll be having greater than 200. So if your problem says that you have a delta value of 200 and above, then you can be clear that you have a ketone functional group. Let's solve some CSIR, gauge, and jam questions based on these chemical shift values. The gauge and jam. The very first question is very recent question, 2023 question, which asks for correct order of C13 NMR spectral shift in ppm relative to TMS. So from TMS, how much is the deshielding they are asking? So the one which is highly deshielded will be having the highest value. Okay. So here they have given the M attached to CH3, CO, and the benzene. We know that in a carbon NMR, the alkyl, here it is CH3, it comes around 5 to 40. Then the one attached to the benzene ring, so benzene carbon will come around 130, and the CO that will come around 160 to 210. Okay, so obviously the delta value for MCH2 will be around 5 to 40, that of phenol will be 130, and that of CO will be around 180. Okay, so obviously the CO has the highest value. It has the highest value. So what is the answer? MCO has the highest, then comes the benzene, then comes the alkyl. So answer 1 is the right option. Next problem is June 2021. What they are asking is, they've given the mass data. Since I have not yet covered the mass, so I may just skip this. They're asking for only one peak in proton NMR and delta 1.4, and one signal for carbon NMR at delta 35 ppm. They're asking what is the compound. Now they've given the four options. Since they've asked for proton only one signal and carbon only one signal, based on that itself we can rule out cyclobutane 1,3-dione. So this is the carbon, and these are the CH2 carbon. So obviously this has two types of carbon. So option A is wrong option. The second one is dichloromethane CH2Cl2. This has one kind of hydrogen and it has one kind of carbon. So we can have this in mind. The next one is cyclohexane. Cyclohexane has CH2, all are CH2, they all are identical, they all give rise to only one signal. And if I also write in the form of char, you'll be having the axial hydrogen and equatorial hydrogen. But since they are flipping, rapid flipping, so I cannot differentiate axial and equatorial for this flipping cyclohexane system. So they'll be identical. So all the CH2 will be identical. So I'll get one carbon signal and one hydrogen signal here also. So that also comes close to what we are thinking. Then comes 1, 2, 3 trimethyl cyclopropane. 1, 2, 3 trimethyl cyclopropane. So obviously here I have two kinds of carbon, the cyclopropane carbon and the CH3 carbon. So two carbon signal. So D is wrong. So now we have B and C. Since the value given is 35 ppm for carbon and 1.4 ppm for hydrogen, it cannot be dichloromethane because the carbon attached to chlorine should come around 60. Any carbon attached to heteroatom will go around 60. So option B is wrong. So the correct answer is cyclohexane. Easy, is it not? The next one. It's GATE 2006 question. They're asking that there is a sharp singlet for one of its proton at delta greater than 8 ppm in the proton NMR, and the signal remains unaffected on shaking with solution with D2O. Since the signal remains unaffected on shaking with solution of D2O, that shows that I do not have exchangeable hydrogen, that is alcoholic OH, phenolic OH, the carboxylic hydrogen, and the amine hydrogen. So I can rule out these options. So option A is gone, option B is gone. Now it is greater than 8. So acetylenic hydrogen will come around 223. So that is also wrong. Then I have aldehyde. So since we know the values, chemical shift values, we're able to easily solve all these problems. Let's go to the next problem. It is asked in CSIR December 2012. They're asking the following statements for 18-annuline whether they're right or wrong. So 18-annuline is aromatic. Yes, it is aromatic. The inner protons resonate at 9.2. Wrong. So for an aromatic system, what do we know? Outer 12 hydrogens are de-shielded, and the inner 6 hydrogens are shielded. So we have seen in anisotropic effect. So with the secondary magnetic field generated aligns near the outer proton and opposes near the inner proton. So the outer protons are de-shielded and the inner protons are shielded. This we have seen already in detail. So now this is for aromatic system. Here I'll cover upon another concept, anti-aromatic compounds. For an anti-aromatic compounds, the outer hydrogens are shielded and the inner hydrogens are de-shielded. For aromatic, outer hydrogens are de-shielded, inner hydrogens are shielded. Just remember, this is very important concept which will be asked in the problem solving for GATE, CSIR or JAM. Okay, so remember this concept. So remember this very clearly. Aromatic outer protons are de-shielded, inner protons are shielded. For anti-aromatic compound, the outer protons are shielded, inner protons are de-shielded. So for aniline, outer protons are 12 protons de-shielded around 9.0 delta. I've already mentioned this. And inner protons, 6 inner protons will be shielded around minus 3.0. Okay. So the second point is absolutely wrong. It is not de-shielded, it is shielded. Okay. So 9.2 is highly de-shielding. Inner protons are shielded, so it cannot be so much de-shielding value. The third option, the 3 6 protons in the shielded zone. Yes, absolutely right. So A is right, C is right. So the option is option D. Next question is from grade 2005. Proton NMR spectrum of 18 aniline gives only one peak at 7.2 for 18 hydrogens. Wrong. Gives only one peak at 5 for 18 hydrogens. Wrong. Two peaks is right, but what is given? 12 hydrogen delta 9 and 6 hydrogen minus 3.0. Yes. So inner you have inner protons are 6, outer protons are 12, inner are shielded. They'll be having lower delta value, outer are de-shielded, they'll be having high delta value. So C is right. So option C is the right answer. D is wrong. So A is wrong, B is wrong, D is wrong. Next question. The correct C13 NMR chemical shift values of the carbon labeled A to E. A to E. So A carbon is attached to oxygen. So it should be around 60. So A should be around 60. So A19 is wrong. A19 is wrong. So option A is out. Next, the B is C double bond O. The ester carbon should be around 160. So here 143 is wrong. So option B is gone. Now you have option C and D. Now you can see here you have the electron withdrawal group. So you have an electron withdrawing group. So this will withdraw the electron. So the D carbon will be having a positive charge. So it should be de-shielded. So I have C carbon and D carbon. D carbon will be electron deficient carbon compared to C. So D is de-shielded than C. So de-shielded means high delta value. So D should have high delta value than C. So here C is 143, D is 125, it's wrong. So D is 143, C is 125 is right. So option D is the right answer. Next problem. They've asked for methyl 4-oxopentanoate. Now this is the structure. Now you can see the methoxy. It should be around 60. So option A is gone, option C is gone. See, always CSI question, if you pick any one reasoning, you can clearly rule out two options. So now we have 50-50 chances. Now we have B and D. Now this C1 is a ester carbon that should be around 170. It cannot be 208. 208 means it should be ketone. So option B is gone. So we have got very simple reasoning. We have got the right answer. So answer is option D. Now let us check. So OM is 51 correct. C1 is 172. C4. C4 is ketone carbon which is 208. And you have C5 which is the alkyl carbon which is 32. So answer is option D. Next problem. Compounds A and B exhibits two singlets, each in proton NMR. The expected chemical shifts are at delta. So they're asking for delta. So I checked the OME. OME should come around. Here it is attached to O followed by C double bond O. Since you have O followed by C double bond O, it is electron withdrawing. Therefore, the O gets a plus charge. So this will be highly de-shielded. So generally the O attached CH3 will be 3.6, but when you have a O followed by a C double bond O, you have electron withdrawal with a C double bond O. This oxygen gets the positive charge, therefore the methyl will be highly de-shielded. It will come around 3.9 to 4. Okay, so the O methoxy should come around 3.9. So the compound B should have the methoxy around 3.9. So 3.9 is right. So option C is gone, option B is gone. Option C is gone and option B is gone. Next you check on to the oxygen of the ester in the A compound. It is electron donating group. It is a plus R group. It is a plus R group. So plus R electron donating in nature. So when you have electron donating in nature, the benzene hydrogen will be shielded. They'll be shielded. Here you have minus R group. They'll withdraw the electrons away from the benzene ring. So here they will give the electrons towards benzene ring. So it will be shielded. Here the benzene ring will be de-shielded compared to A benzene ring. So A benzene ring should have lower value. Shielded means low delta. De-shielded means high delta. So benzene has a range of 6 to 8. So 6.9 for A and 7.7 for B will be exactly right. It's not so. So the 7.7 for A and 6.9 for B. So 7.7 for A and 6.9 for B will be wrong. So the answer is option A. December 2012, they've asked for the para-hydroxybenzoic acid. When I see the carboxylic carbon should come around 170. Is it not? So carboxylic carbon should come around 170. Therefore, I have option B and D which are in pick. I've picked them. A and C I've ruled out. Then you can see that the carbon 1 is 122. So this is carbon 1, 2, 3, 4. Okay, 5 and 6. So carbon 1 is attached to C. The carboxylic acid is given as 122. Now they have asked to compare the carbon 2 and 6 and carbon 3 and 5. Carbon 4 is 162. So the carbon 4 which is attached here, it is attached to an oxygen. So it is 162. It is benzene carbon which will come around 130. But since you have an oxygen which is electron withdrawing, it is withdrawing the electron, making the carbon of the benzene de-shielded, comes around 162. Okay, now fine. So we have to find out 2 and 6 carbon and 3 and 5 carbon. Now see here, this OH is a plus R group and the carboxylic is a minus R group. So the minus R group will make the auto and para position positively charged and the plus R group will make the ortho and para position negatively charged. So 3 and 5 should be shielded. 3 and 5 should be shielded. 2 and 6 should be de-shielded. Very simple. So 2 and 6 should have high delta value and 3 and 5 should have low delta value. So based on that, just pick the answer. So 2 and 6 should be high delta. So 2 and 6 should be high delta. 3 and 5 should be low delta. So answer is option B. Is that not? Next problem, December 2011. They have asked to find out the chemical shifts for proton A to D. Okay, D is O methoxy attached to a C double bond O. It should be around 3.9. So D is 3.9. So option here I have an option where I have 3.9. So based on that, I can rule out option A and C. So A is wrong, C is wrong. Next you have the carbon C 2.1. So it is C 2.1, that is okay. Now we have to compare between A and B. Now you see that I have electron withdrawing group. So since I have electron withdrawing group, the carbon B will have a positive charge. So since carbon B has a positive charge, the hydrogens will be de-shielded. So since this is de-shielded, it will be having high delta value compared to A hydrogen. So B should have high delta value compared to A hydrogen. So what will happen? Option B is ruled out. So option D is the right answer. Very simple question. Just match the carbon chemical shift with the compound. I will pick acetone. I love this molecule because it gives a very easy clue. It's about 200. Therefore, C is 4. C is 4. C is 4. C is 4. So option B wrong. Option D wrong. Next, I will pick, okay, acetic acid I'll pick. So since acetic acid comes around 170, so A is 3. A is 3, I have here. So option A is right answer. Very simple. I have quickly done that. So aromaticity. So in homoaromaticity, the conjugated system bypasses a sp3 hybridized carbon because in aromatic system you should have all the carbon should be having an unhybridized p orbital. Since sp3 hybridized orbital cannot have conjugation, so it is picked away, it is bypassed to have the aromaticity. Okay, so when I have this, it becomes aromatic. Now hb falls in the inner zone, ha falls in the outer zone. So ha will be de-shielded since it is following in the outer zone, and HB will be shielded because it falls in the shielding zone. So B will be shielded, B will be having low delta value. So B will be minus zero point 0.3 and A will be 5.1. So B is, that is P. P is 5.1. P is equal to 2. So option 2 gone, option 3 gone. So option 1 is there, option 4 is there. Now Q is 1. Q is 1. So answer 1 option is the right answer. Interesting question, December 2017. This is having 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So 12. So it is anti-aromatic. Now here I have 1, 2, 1, 2, 3, 4, 5, 6, 7. So 14 electrons. So it is aromatic system. Aromatic system. This is anti-aromatic system. Okay, so anti-aromatic, and so anti-aromatic will be having inner protons will be de-shielded. For aromatic system, the inner protons will be shielded. So shielded. So since you have 1 equal to B, 1B means I'll be having option 1 gone, option 4 gone. So now 1B, and we know that 3 is aromatic system. Aromatic system will be having inner proton shielded. So 3 should be having a value of minus 0.61. So 3 will be C. So option 3 is gone. So answer is option 2. And this is an alkene system which will come around 4 to 6, which is 6.72. So 2 will be June 2014 question. You have three kinds of system. So this is negatively charged, positively charged. Positive means de-shielded. Negative means shielded. And we know the benzene comes around delta 7.2. So 2 is 7.2. That is without any reservation, without doubts, I can say 2 is 2. So I can rule out option C and D. So now A is, now 1 is shielded, so it will be having low delta value. 3 is D shielded, it will be having high delta value. So now look into the option. So option A is the right answer. Next is JAM 2016 question. They've asked for the correct order of proton NMR chemical shift value for the labeled methyl groups. So I have methyl 1, 2, 3, 4. As we can see, the methyl is attached to an heteroatom followed by C double bond O. As I've told you, when I have a methyl attached to a heteroatom, that is oxygen, methyl attached to oxygen will be around 3.6. If it is further attached to a C double bond O, it will be highly deshielded. It will come around 3.9. So this will come around 3.9. And the methyl, which is alkyl methyl 3, which will be around 1.5 something, so it will from 0.5 to 2. And the methyl attached to alkene carbon is 1.7. The methyl attached to the benzene ring will be around 2.3. So now as we can see, the methyl 2, which is highly deshielded, will be having the highest value. So option A is gone, option D is gone. So if you pick one correct reasoning, you can rule out two options. So you have 50-50 chances. Now methyl 3 is highly shielded, it comes around 1.5. And methyl 4 is 1.7, methyl 1 is 2.3. So the order is methyl 2, methyl 1, methyl 4, and methyl 3. So option B is the right answer. The next is JAM 2021 problem. They've asked for the correct structure of the compound. The values are 7.31 and 7.2, which comes in the aromatic region. So aromatic region, 4 hydrogens are giving the signals. So 2 hydrogens are missing. So 2 hydrogens are substituted. So it is a di-substituted compound. It is di-substituted compound. First clue. So I'll rule out option A based on this. Next, in aromatic region, you have only 4 hydrogens in aromatic regions. Among that, you have only 2 signal. 2 signal in aromatic region. But look at the compound C. You have 4 hydrogens, and for all the 4 are in different environment. This hydrogen has nearby methyl, this hydrogen nearby CH2Cl. So I'll be having 4 hydrogen signal in aromatic region. So option C is also wrong. Now among B and C, the methyl attached to aromatic ring will be around 2.3. They have asked that. Okay, and the two hydrogen, CH2 hydrogen attached to chlorine on one side and benzene on sp2 hybridized benzene on other side, it comes around 4.5. Whereas this compound CH2, CH3 attached to a benzene ring, this will come around 2.3, not 4.5. Okay, so D is wrong. So option B is the right answer. Last question. They've asked for the shift in resonance of the given proton from TMS provided the chemical shift is 2 ppm. Next is JAM 2017 question. They've asked for the shift in resonance of a proton from TMS. Okay, and we know that the chemical shift is 2 ppm. So we know the formula for delta. Delta is equal to delta nu by nu of the instrument, where delta nu is the shift of the sample from the reference, which is TMS, followed by the operating frequency, which is given in megahertz. So the numerator is in hertz, denominator is in megahertz. So it is given 350 megahertz. So now the delta is 2, delta nu, I don't know how much is the shift, and the instrumental frequency is 350 megahertz. So the delta nu in hertz will be, so megahertz, hertz, this is in ppm. So I'll be having the delta nu, which will come as 2 into 350, which is 700 hertz. So the answer is 700 hertz. Very simple. Hope you have understood all the concept in this particular video with clarity. If you have any doubts, you can post that in the comment section. Next video, I'll talk about spin-spin splitting and the problems related to that. As a learning check, I'll be posting a Google form in the description. Try to solve all the problems and submit the Google form. If you want to watch videos of similar type, kindly like, share and subscribe the channel. Thank you so much.